All right. Welcome back, everyone, to day 3 of What's a Microcontroller with Python and the Microbit. Here, as always, is a link to the slideshow that's going to have almost, if not all, of the links I followed today. I'm going into the chat and pasting it. And then now I'm missing the little indicator that says that my screen is being shared. Did I possibly share the wrong screen? Is everybody looking right now at the cover slide for the slideshow?
Yes.
Okay, good. That's very unusual. All right. So let's see. You've got the okay. Thank you. So you've got the slides. And then, so the next thing, as always, is if you have a single screen, there's going to be a little view button in the upper right of your Zoom. You may have to kind of wiggle your mouse around in front of the presentation that's probably taking your whole screen at this point. And then click View and select Exit Full Screen. After you do that, you can go ahead and resize the presentation. And then, basically at certain times you can hit maximize and it'll take up the whole screen. And then you can hit and then it'll the maximize button will change to I forget what they call it, but where it's just a normal window size. And then of course there's minimize as well. Then make sure to connect your microbit and to your computer, and also start up a version 2 Python editor, python.microbit.org/v/2. I'm pasting that into the chat. There you go. All right, so today we'll finish up push buttons and then experiment with servos and the potentiometer and talk about some other resources that are available to you. For follow-ups, the first one, and I want to emphasize that we've talked, there have been some questions that have come in from expert level questions. And so if you're new, try not to worry about that, because what's in the book should pretty much suffice. But there's a lot of folks that or there are several teachers who need the extra information. And so the first one is for Ricky, and this is, but may apply to several of you. And what this is it's in tech.microbit.org. This is their developer site. And what it is it's the edge connector pinout. And there's more to it than just listing the pins. What we have here is it shows, like, if we look at socket 0 here on the microbit, or pin 0, that is an analog, or can be an analog input or a digital input, and it's P0. Then it'll also call out P4, for example, can be an analog input, but is normally busy controlling the LED display along with P6, P7, and etc. So this lists the functionality of all the different pins. And then there's actually more information down here. And you may have noticed in some of the scripts where it says set pull, set underscore pull, and then pin number, no pull. And the reason for that is because there are some pins, like, let's take a look at P1 here. By default, P1 starts up with a 12K resistor connected to ground. So that joins the party of any circuit that that you might connect to that. And so you'd have to know, if you didn't want this 12K resistor to interact with the circuit, to tell it no pull resistor of any kind. and it initializes as an input. Likewise with P8, for example, that's another one that initializes as an input. It has a 12K pull down resistor. And here's a 10K pull up resistor. And again, these are the initial values, and it has a lot to do with the fact that push buttons and the LED display are shared with these pins. And so like here's button B, that's P11. And so with P11, it's kind of hard to avoid sharing with a push button. And so it's good to have this information about what's on the microbit so that you can find a pin like, pin 0 is obviously nice and empty. Pin 2 is obviously nice and empty, and so on and so forth. But some of these get a little bit more complicated. And the easiest thing to do is just to go for the pins that don't have any extra features initially. Some of this I2C stuff is in my mind a little bit arbitrary. There's some special features up here. I have pretty much ignored them. Basically, you'll see that, oh no, pin 16 is empty. Yeah, so 13, 14, and 15, although this is used with, they're expected to be used with a communication protocol between the microcontroller on the microbit and another chip, but they work just fine as normal input-output pins for controlling LEDs and reading push buttons. So again, don't let that discourage you. If you're a beginner with electricity and electronics, focus on what's in the textbook and go through it yourself at a more detailed level after this whirlwind tour that we've been on. The second one was for Carol, but for any Linux users, I just added a search for how to install a Chromium browser on Ubuntu, and you get a bunch of links with step-by-step instructions for how to do that. And then after that, Ari has reported some that he's been using Chromium with the Raspberry Pi, no problem programming a microbit with the python.microbit.org editor. I guess I'd like to take a show of hands. We can loop back around to more about push buttons, or we can dig into this first before moving on to the servo and the dial that or the control knob that you installed. So I would like to see a show of thumbs up or thumbs down for how many of you would like to just kind of dive into the servos and then loop back around to push buttons, and how many of you would like to do push buttons first, talk about those. I'll try to make it brief, but I know myself, I'd be kind of excited. I just installed these, new little things on my board, and servos, push buttons done. Any other opinions? Okay, so anybody who wants to go servos and potentiometer next, give me a thumbs up. 1, 2, 3.
My head's already rotating from what I did yesterday.
Well, okay, we'll get ready to have it spin even faster, because here we go into servos. First thing about the servo, a servo is a motor that you can use to move to certain positions. So looking here, you'll see that there's a signal going to the servo from the microbit, and depending on the signal, the servo will turn to and hold, and you can even press lightly against this. It's called a horn, this little armature. The servo horn is the common reference. And it looks kind of like a horn, if you think about it, the single armature at any rate. And so based on the signal that gets delivered 50 times a second, whether it's very short like you see now, or the high signal lasts longer and progressively longer, you'll see that the servo turns to and holds a further counterclockwise position. So first thing we do is test the battery pack. And I think that's a good thing to do. We want to make sure that we've got that connected to correctly. And so, but since we've already connected it, I'm a little hesitant to disconnect it. So instead of testing the battery pack, I would like to instead go through and verify that we've got everything connected just so. So the first one I'd like you to verify is take a very close look at your board and make sure that the center pin of the 3-pin header that you plugged in is connected to a socket that's close to the red line. The bottom pin should be connected to a socket that's close to the blue line. And then the topmost pin should go through a red, red, brown, gold 220 ohm resistor to the same row as P16. So let's all look at that very carefully. It's important to make sure that that is exactly right. So once you've double checked that, it'll probably look more like this with your, so then the next thing you want to check is that with this black wire going between next to the blue rail, which is ground, to row 5, you want to make sure that that's going to the brown wire of the 3-wire cable. And of course, the row 4 to the red, to a socket by the red line, that should go to a red wire. And then the resistor should be on the same row as the orange wire. So double check those things. And then again, the other end of the resistor needs to be in P16. And boy, do I ever like the magnifying glass and the making everything else translucent. Because it really helps us focus on a certain part of the circuit. And so this is more or less what it'll look like. Next up, it probably is still a good idea to check the batteries. So the main thing I want you to do is, like, if you smell heated plastic at any instant during all this, be prepared to disconnect the battery immediately. I don't think we're going to have any problems, but also I think actually that this is a situation where we want to make sure that the 2 probes are not touching each other. So make sure that the metal of the 2 probes that you have are not touching each other. And after that, go ahead and plug the alligator probes into the left and right sockets. And what we're going to do is put batteries in the battery holder and measure the voltage. Did I dwell on that long enough? So make sure the metal is not connected to each other here. And then put the probes into the red and blue, a socket by the red line and a socket by the blue line. Okay, and then I'm going to give you a link to measure volts that you can download and then open with your Cyberscope.
1 second. On the bottom, which one is the black and which one's the red? Is
Okay.
it P0 is the red or the black?
Since we're just measuring, it won't matter, aside from that you'll get a negative measurement if you have them reversed. But the black alligator clip should be connected to P0,
Okay.
and you're welcome. And the red alligator clip to P2. And then you want to use the red end to probe the red cable and the black wire to probe the or the socket by the red line, and the black wire to probe the socket by the blue line. And so what we're going to do next, and I pasted it in already, is test our battery voltage. And so a recap of doing that is you'll go to the page, right-click Measure Volts and select Save Link As. Let it download. Drag it and drop it onto your python.microbit.org editor. Click Connect, Flash, and then disconnect. Then go over to your Cyberscope, cyberscope.parallax.com. I'll paste that into the chat. And click Connect. Now, I actually am behind you guys. I haven't connected. I guess I'd better get mine connected properly here. And it might not show anything because we haven't put our batteries in yet, but I'm at least going to match your connection so I can see what you see.
Andy, I'm so sorry, but the link that you sent for the hex files, I'm having a hard time getting to the link. It's just giving me like zeros and
Yeah.
ones. And
Same.
Okay, so the important thing is that you want to right-click the link, or well, first thing, right-click the link, click Save Link As, and then save it. It's going to appear in your Downloads ribbon here. Now, then you want to have a python.microbit.org editor open. And I'll give you an alternate route. I just want to check and make sure that this is what's not working. So what?
I don't actually have the ability to save it out of the chat. I only have the ability to copy it out of the chat or open link.
same for me.
Okay, so what I meant to do, and I might not have done it right, is I meant to give you a page to go to. And so once you open that page, then my hope is that you'll be able to save did I like paste in a link to?
Yeah,
The
it's
hex file. Mhm.
direct link to
So
the
this-
file, I think.
Sorry about that.
Yeah, this new link is working. Thank you.
Okay, thanks. Thanks for letting me know. I'm sorry about that. Okay, so yeah, so let's see here. One thing I don't understand is why it doesn't appear to be working for me here. Disconnect. My Cyberscope is behaving a little bit unusually. I'm throwing batteries in the battery holder just to see if that does anything different.
Yeah, and we have a report of dead batteries too.
Okay. Yeah. Let's see here. Oh, this is a little scary. Okay. I'm checking to see if the microbit is properly sending data, and it does not look like it is. Not seeing any data at all. Okay, so I got to try to figure out what I'm doing wrong here.
Could it have something to do with that particular file being a second file rather than the original one?
Yeah, I mean, it's possible. It is possible. So let's see. I remember measure volts from yesterday. I'm going to go grab it real quick just to see if there's some kind of issue with. Okay, so let's see. I think in electrical measurements is where I got it before. Measure voltage. Script. Flash. Okay, so that message you just saw was because I forgot to disconnect from the cyberscope. Okay, now if I connect, all right, so I'm going to try disconnecting USB from my cyberscope and then reconnect it. Connect, select. All right. Let's try one more time. V2.
I had some problems with that yesterday and I ended up having to do a hard disconnect, pull the plug out.
Yeah, that's what I just did. And interestingly, yeah, this is sometimes something that I see when Chrome has been updated. Because it's not even letting me load the code into the microbit. Well, while we're on this topic, let's talk about how to load code into your microbit using the file explorer. One of the things you can do is when you have your microbit plugged in, it looks like a flash drive. And so you can actually go to your downloads and then drag and drop the file onto your microbit. It takes longer to load because it's transferring the entire file. Not that this is going to do us a lot of good. I'm going to try just to get myself unstuck. How many of you are stuck in the same way I am? Have any of you got your cyberscope working? Okay, Kurt is having the same issue. Yeah. And let's see, Carol, are you having the same issue or are you up and running?
Now I'm up and running.
Yeah, and then Christine says, I don't see anything. Okay. All right, so let's try version 3 just to see if possibly there was a Chrome update that broke something in version 2, but not in 3. It's just a hypothesis. I really don't know what the actual situation is here. Okay, send to microbit. It's going to take extra long the first time. Select it, connect. Then send to microbit should flash it. Wow. Okay, this is going to be a rather uninteresting course if we can't get this fixed. I'm going to try refreshing and just loading in the hello world default text.
part of the time that I had some of the connection problems,
Mm-hmm.
it seemed like it was because I hadn't changed, or the name of the text file didn't change up in the title where the script is for the title.
Hmm.
And it often default back. So every time I tried to flash a file, I'd end up getting the hello world as a default on there.
Okay, so what I've done now is I've removed my microbit completely from the okay. Yeah, all right. So it looks like I've got a it looks like my microbit is recovering. I'm hoping that everyone here doesn't have to go through quite all this. So I'm going to switch back to version 2 and just show you a couple of suggestions. And I'm hoping that that'll get us all back to a functioning microbit. All right, so the first thing I did is I removed the microbit from the edge connector. And I also unplugged the microbit from the USB cable, counted to 3, and then plugged it back in. Okay, after that, I did something that's fairly universal. I'm going to go back to version 2. Okay, so the next thing I did was close that. Let's see here. Okay, up next to the refresh and homepage button in your Chrome browser, there's a little lock. And when you click it, it'll allow you to remove the web USB connection. So we're revoking access. And when we close the window, it'll ask you to reload the page. Okay, then after doing that, that's the time to go and unplug your microbit and then plug it back in. And what we want to do is not try to run that other script just now. All we want to do is run the default script. So try clicking connect, selecting your microbit, and then flashing that default script that the page loads with. And unlike mine, yours should still load kind of quickly. And then once that's done, once it's done loading, we'll be able to see a little hello world message scroll across the microbit. Hopefully. Okay, so I'm getting the hello world after having done all that. How about you all? Thumb up from Kurt. Good.
Yeah, mine's working. I'm able to see the hello world.
Okay, Christine gives me a thumbs up. Anna, thumbs up in the chat. All right. Well, that's a good lesson in troubleshooting, although normally it's only one call from a it's a rare call from a teacher where I'll end up walking through these kind of steps. I guess it's good that we had the challenge. Now, I'm probably going to shy away from opening a Cyberscope thing until, well, I really want to see if this works. Let me break my own browser here and before suggesting that you do it yourselves as well. All right, so I'll try loading again the measure volts script, flash it. Disconnect, go over to Cyberscope. Connect to the embed serial port, and now it's working. All right, I'm going to give you this page just in case it's something about that that other script. So we'll have you download this script instead. So there's the page with the script on it. Wait a second. Yeah, so that's the measure volts with Cyberscope script. So go ahead and try that again. And it's not going to show anything until I plug it back in. So here we go. 3.2 volts. That's exactly what I want to see. And then if you take a battery out, hopefully, yeah, it goes down to 0 volts. So put both your batteries in.
Hey, Andy.
Yeah.
I was using the this measure volts script from a couple of days ago, and that's why mine wasn't working. As soon as I did the measure volts with Cyberscope, it worked and it was perfect. So that was at least the issue that I was having.
Okay. Yeah, just off the top of my head, this one is kind of mysterious. I just wonder, maybe a server got reset somewhere. It might have even been, you know, the python.microbit.org editor's server had a, you know, I really don't know. Might have been the Cyberscope. I'm not
The
sure.
original script had terminal in it as a value, and you had to change that to Cyberscope.
Yes, and then
Work.
and then the ones. So what Carol is saying is yeah, that the very first measure volts we use the terminal instead of the actual Cyberscope, and so in this script that we used, it is set to Cyberscope. But the good news is that we're all back up and running. I hope. Jump in if if one of you is still down. All right, so so we can see now that our batteries have about 3.2 volts. That's not 3.3, but it's pretty good. Those are definitely nice, new, shiny batteries straight out of the microbit kit. And so once you've verified that you have upwards of 3 volts connected to your servo supply, now we can go ahead and try something with the servo. So connect and test the servo. So we already double checked our connections. And I'll just go back and that was with the little magnifying glass to look closely at our servo connections. And after that, there's a nice little script that will have it point in multiple directions. But just before we run it, one last formality, and that is what we want to do with the servo right here is find out its gently rotate the horn, and your horn might be somewhere off in the boonies. So wherever you end up where you can feel that clockwise, the stopper inside the servo prevent you from turning it anymore, just leave it there. And once you've got the servo turned all the way to its clockwise limit, then you can take the horn back off and put it just a little bit low, pointing straight to the right. So maybe just a couple degrees below, straight to the right. So that's probably about the natural clockwise limit of the servo if you're going to use it to point to 0 degrees like that. And then you can also bring it around, and you want to see it pointing downward at about the same angle at its counterclockwise limit as you do at its clockwise limit. So again, just make sure that you've got that servo horn on so that it's pointing, instead of pointing straight to the right, maybe downward a little bit. And then it should be approximately the same when you rotate it to its counterclockwise limit. Okay, are we all ready to move to the next step? Good idea using the battery holder, thank you. I'm not sure it's working quite yet, but the cable has a lot of spring in it, unfortunately. Well, I'm just going to leave it on its side for now, and I'll hold it when it comes time to demo. Okay, so the next thing we want to do is disconnect our cyberscope. And then I'll go ahead and paste you in some test code. And this test code should go to 0 degrees, that's pointing straight to the right, 45 up and to the right, 90 straight up, and then 180 straight to the left. So there's the code to try out. Connect, flash. And so now in a loop, here's 45 degrees, there is 90 degrees, plus or minus, 180 degrees, going back around to 0. Doesn't have to be exact. Roughly 0 degrees, roughly 45 degrees, roughly 90 degrees. And you could actually, like, you know, if I think I might on this one just take the horn off, and maybe if I wanted to be a little bit more precise, I'd take the horn off and and rotate it by maybe one tooth on the little shaft that it's pressed onto. And then I might also adjust the values in this script a little bit just to get that 128 to go to exactly 180. And there's a little trial and error for students who like to have things be super precise. But I think that's a good first cut. How's everybody else doing? Have you got your servo pointing to those directions? You're still working. A few thumbs up. Oh, a few more thumbs up. Good job, everyone. All right. As usual, just give me a shout out if you need any help. So let us now take a look at how it works.
We have a couple of questions in the chat. One isn't responding at.
Okay, so what was that, Ari? Mine isn't responding at all. Okay, so for a not responding servo, step one is check to make sure your batteries are in the right direction. Step two is to take a battery out. Oh, well, okay. Before taking a battery out, step one is to make sure that your script is loaded. So make sure that the script is loaded and running.
My students also, when they have this, it's usually when they have the servo wires backwards, like the yellow, orange, red. I mean, the yellow, orange, brown.
Yes.
They'll have those backwards.
Thank you. Excellent point. So that's definitely a thing. You want to make sure that the brown wire is low and the orange wire is up high. I guess another question is, were you able, okay, do we need to put the black and red wires to the servo? Yes, you do. So so that the answer to, or so that question, let's see if I can get back to the connect and test the servo. So that was part of the double checking this wiring right here. Is this shows where the brown, red, and orange cables are, and it shows where the black wire goes to row 5, between row 5 and a socket next to the blue stripe, and then the red wire goes from row 4 to a socket next to the red stripe. Then you've got to make sure that the brown wire is connected to row 5. Another thing is make sure that this 3-pin header is well inserted. It has to be all the way into the sockets. Likewise with your resistor leads and your jumper wire leads. They all need to sink in by, say, 1/4 inch to really be connected. Then, barring all that, the next thing to do is hopefully your battery measurements came out okay with the Cyberscope. And you'll want to take a look at, okay, one new message. Okay, so Anna, have you had any, has any of this fixed it for you? Oh, good. No, still not working. All right, so next up, what we want to do is take out one of the batteries. Then take your servo and gently rotate that horn. Does it move? Okay, so it does move. All right. And then the other important thing is going to be with your battery pack. You've got to make sure that the flat end of the battery goes up against the spring. It's also marked with a negative on the little green cellophane that wraps it. And let's see what else could be in the way. The other thing we could do is just make sure that your microbit is working. So you could display dot scroll hello. Let's make sure that works for me.
You have a type on display.
Oh, Dispali, thank you. Sometimes my left and right hands get ahead of each other there. Okay, so so that would be the next thing to do is right after from microbit import star. Let's go ahead and add the line that I'm pasting in. Batteries are in the right way. Thank you, Anna. So flash the modified program and make sure that it's running. I guess another thing is you got to make sure that you're connected. So you got to hit connect if it says connect, you got to hit connect so that it shows disconnect, and that means you're connected. My microbit is scrolling. Hello. Wow. So your servo is just not responding. I think we'll have to do the rest after the session and get you troubleshot then, or maybe during the break, if you can hang with us, we'll try a few more things.
Yeah, Anna suggests the same.
Ah, good. All right, so here's a fun one. I think I'm going to do a more topical treatment of this because I want you to try a few fun things and then just be aware that there's going to be a lot more material that's within the chapters. And Anna, go ahead and try this just in case something comes right. Okay, I just pasted in a script that we can run and then open the serial terminal and type in an angle and then have it respond with that angle. So we're going to flash that and then go to the open serial button. And you might see an enter value down at the bottom. You can actually, to clean it up, you can hit close serial and then open serial again, and it'll say enter values in the 0 to 180 range. And so I'll try, looks like my servo right now is at 90. So I'll try 0, and I want to see it point to the right. Nice. And then 180, and it'll point to the left. 45. We've got some nice console control here of our servo.
Andy, what's the Y that it's displaying? What is that about?
Oh, I'm glad you asked, Kurt. That's Kurt, right? Yes. Was that
Yes.
Kurt that asked? Okay. I'm glad you asked. It's because I'm skipping around. So what this is after trying out the 4 angles, so these guys, and then adding that 135, students are challenged to do that. And then what we do is we say, well, you know, that 26 for 0 degrees and that 51 for 45 and the 77 and 128 for 90 and 180 respectively don't make a whole lot of sense. So why not come up with something better using a little bit of math? And so this is an excuse for solving for 2 equations and 2 unknowns. And so basically we say, Well, what we have is a range of should be 26 to 128, and that maps to 0 degrees to 180 degrees. And so then what we do is we say, okay, well, those are two different X's and Y's. And then we go through and say, okay, well, then what would my M and my B be, so that for an X that's in degrees, I get a Y that's in the servo number that we need to make it turn to that number of degrees. And to not belabor the point, we go through all of the math and come up with Y equals 0.5689 plus 25.6. Sorry, Y equals 0.5689x plus 25.6. Now, looking at the script, this is actually coming from a script. The students are challenged. It tells them they had to start by using a Y value. That is, they had to use 26 to 128. And that's the working script they were given. And so the challenge was to change that script around so that they use the, so it was printing the degrees. I'll go ahead and get you the actual script so you can see what they started with. Or actually, let's see. I think it was in how it works. There's a try this. Must be on the next page. Oh, the equation, yeah, it is on the next page. So what they started with in terms of working code was the inverse. So they started with this one. And this one shows you let's try pasting that again, copy. Paste. There we go. So the initial terminal control servo, instead of entering degrees, the students are entering those numbers between 26 and 128. So you can try that and just keep in mind, you might want to save this one as like degree controlled servo in case you want to reopen it. It is also in the slideshow. Basically, it's a hidden Easter egg underneath slide 55. Okay, so load save, download project hex. Okay, so now that we have a copy of that, we can paste over the other one and flash it. And so what it shows is that if you type in 26, for example, in terms of degrees, it says you're getting about 7 degrees out of it. Let's see what 25 gives us. Nothing. See here, and then 128 gives us about 180 degrees. Oh, 0.7 degrees, pardon me. So close to 0, close to 180. And so this is basically introducing how y equals mx plus b can be used to map a value from a range that's not very, easy to relate to one that's more familiar, that being the degrees, the degree measurements. And with that, we should go ahead and take a quick break and also help troubleshoot on a servo. So go ahead and please rejoin me at 7 minutes past the hour. or go ahead and hang out. And Ari, if you could pause the recording. Okay, so just a quick update. We got a text from Anna. Thank you for letting us know. There was, I guess the resistor was plugged in maybe one row off or something like that. And so Anna's servo is now working. And then another question came up during the break about how to remove the JST, Japan solderless terminal plug from the socket on the breadboard once you've, or on the edge adapter after plugging it in. It's really difficult to pull it out. So my main recommendation is to just simply leave it connected always and just take out the batteries when not in use. So that's really the best way to disconnect your batteries, is to just remove one or both. It is fair game to just remove one. Then you're not conducting any current through the batteries. It's an open circuit. Now, for those of you who really do need to get the plug out for whatever reason, the most important thing is you want to hold on to the socket and then grab the little wings that are sticking out of the plug, and then just kind of start wiggling back and forth, and it will come out. But you might notice I actually bent the socket a little bit when I did that. And it's okay to just bend it back. It should be fine. So I try to minimize the amount that I plug and unplug this little port. It has little catches in it that make it permanent for things that are inside, say, a box, where you'd open the box and stick the batteries in and then close the box, and then like a standard or a product that's battery powered, and it might have built in this kind of connection, and it's a little bit too grippy for students to normally unplug. So definitely just plan on removing the batteries when not in use, and leave it connected like this is the best way to go. And we're also looking into redesigning that so that if we can find a connector that does not have a latch in it. All right, so let's do one more, a couple more fun things with the servo. Now that we've got numbers to control the servo's angle, the next thing to do is we could try push button control, where a script checks if a button is pressed, and if so, the push buttons, these two guys, can be used to make the servo rotate in one direction or another. And so this is an activity that students try, and oopsie. And the students get to work a fair bit with conditionals, that being if statements, in this script. Here you go. And
we have a question from Carol asking if you can make your mouse pointer bigger. Not sure how fast we.
Yeah. Let's see here. How's that? Okay, Carol, is this okay? Is that more visible? I see you still squinting. This is the largest I can get it. Does it? I mean, to me, it's huge. Or it's fairly large. Can anybody else see it?
Can you run it across the screen again?
Oh, maybe this is a Zoom thing.
Yeah, because it's tiny, but I can see it. Sometimes they have effects like you can make make it a different color.
Uh-huh.
Honestly, I think I would be using a pointer in real space, like a pencil to point at different parts of the board.
Yeah.
It might be awkward for angle purposes, but
True. But what happens when I need to point at something on the screen?
yeah.
Yeah. Okay, so I'll try to just call out where my mouse pointer is.
Maybe it has, oh, I'm muted, aren't I? Oh,
No,
not.
we can hear you.
Maybe it has something to do with my age.
Well, I mean, I remember my
No,
mouse.
it's pretty tiny. It is. pretty
Yeah, my
Yeah.
mouse pointer used to be pretty large. So this is kind of a new development here. If anybody knows off the top of their head where to adjust that in Zoom, because it looks like even if I adjust it in Windows, it's not coming through on Zoom. And so if anybody happens to know off the top of their head, yeah, we're gonna have to just suffer through that one this time. Anyway, so the thing to do now is to I think you might want to set your alligator clips aside for this one. And you can press the, I guess I might not have loaded it, flash. There we go. All right, so now the lower button will reduce your angle and the upper button will increase your angle.
Is this still under terminal controlled servo?
This is one where I pasted it into the chat.
That's what I thought I picked up.
Okay, I'm pasting it in again just in case.
Oh,
Whoa.
says servo buttons control.
Yeah, that's the one.
Yeah. It didn't, okay. It didn't copy and paste this time. Well, I'll go old fashioned. Control C.
Oldies but goodies. So interestingly, there's only one analog right call that sets the servo position. All the rest of it is checking, first of all, for whether or not, or checking the buttons, and then checking if one of them is pressed, adding one to the value, and then checking to make sure the value doesn't try to make it turn past its mechanical limitations. And so so it does a lot of work with the number of value before giving that value to the right analog method. Down here on line 25. There's another fun one I'd like to bring to your attention. And you can try this one on your own. What it is basically you can, if you hold the servo as you're seeing in the diagram here, the built-in accelerometer gets XY axis measurements so that the microbit can know its orientation in space. And it can use those axis measurements to set the angle of the servo so that if you're holding it as shown, it always points up. Thought that was kind of a neat one.
We have a question
Yes.
for Nilu about code. What is set underscore analog underscore period 20?
Okay, good question. A servo, and this is actually in the how it works section, and then there's also a section where we measure the servo signal with the cyberscope. And so the servo signal needs to be repeated, this pulse that dictates the position of the servo. This pulse needs to be repeated every 20 thousandths of a second, or every 50 millisecond, or pardon me, or 50 times a second is another way to say that. And so Nilu's question was, well, gee, I see this pin 16 dot set analog period of 20. What is that? And so the answer again is that sets it so that these control pulses, which is what they're commonly referred to as, repeat themselves every 21 thousandths of a second. Okie dokie. Now there's also measure servo signals, and this is where we get into, and so we use the red probe to look at P16, and then there's a script to plot the servo. And when you run it, you will actually see that this is the narrow pulses, and then you'll see them get wider as the servo moves to 90, and then wider again, or to 45, and then wider again as it moves to 90, and wider still as it moves to 180. And we talk a lot about how that signal is categorized, and we have a period, which is the period of time for the signal to repeat itself. There's a rising and a falling edge on the signal, and then we use the oscilloscope to zoom in more closely on the control pulse to measure the actual amount of time. And so here, this is 90 degrees. It's 1.5 milliseconds, or 1500 microseconds, millionths of a second. And that pulse is the one that you would see for 90. And so you'd actually see it right here when it was 0, right here when it's 45, here when it's 90, and then probably out here when it's 180. And now let's do some potentiometer sensing. So I think that we want to start with a couple of activities in. And if time permits, this, by the way, is a draft. I'll go ahead and paste you in the, yeah, measure pen. No, in fact, we want to go further in than that. Plot. No, I guess it is measure potentiometer angle. So here's where I want to start. Basically, there's a lot of extra activities before this that students follow along with to understand what's inside the potentiometer and how it works. But let's start with this simple little script right here. First of all, I'm going to copy you. See here, this is the script inside measure potentiometer angle with A to D. Here we go. So I'll give you this link, and it should take you to that spot in the document so you can see where we are. This document is very close to being posted. I think Stephanie's been posting pieces of it, and I still have the questions, exercises, and projects to fill in, and maybe one final activity. Let's see, so I pasted that in, and then we're going to paste the test code in. There we go. So this is a Google Doc draft. And the reason it says node at the top of a given activity is because that is to that's an internal thing that's used for posting it to the web. And this is one where you're going to flash and then open serial. And then you don't need to use a screwdriver. You can just use your fingertips. I'm going to use a screwdriver so that it's easier to see it rotating. And I also have to get back to my camera brightness. There we go. So notice that as I turn the potentiometer clockwise, the number gets larger. And eventually I'm going to feel a limit. There it is, pretty much straight up and down with the little slot in the potentiometer. And we're pretty close to 1024, which is the highest voltage you would, or 1023, which is the highest voltage measurement you would see. It's measuring voltage on P4. And we can turn it the other direction and get all the way to 0. And now I have it kind of in the neighborhood of the halfway point. 512 would be roughly halfway. 514 is close enough. And so go ahead and give me a thumbs up when you're able to get your limits close to 0 and 1023, plus or minus 50. And then also can kind of see some various values in between. Good job, Anna. Excellent, Christine. Eric, fantastic.
What the resistor was going from the potentiometer to P4, correct?
Correct, yes.
All right. So my numbers are jumping around all over, so I might have something loose.
Try pressing down on the potentiometer. It needs to sink in. Sometimes it'll pop back out. Try pressing it down nice and firmly.
Yeah, it did go down. Now I'm gonna see if I just moved it. It's not reading, but I'll figure it out.
Okay. All right. Well, so there's a lot of things we can do with potentiometer control. And I guess first of all, I just want to mention that for the preliminaries, the students learned first off that there's a certain rotation range with a counterclockwise and a clockwise limit, adjustment knob, and then 3 terminals that are labeled A, B, and W. And W is for wiper. And then they go through finding the parts. And the first thing that they did that we're not going to do is they reinstated their resistance meter circuit. And then they actually went in and measured the resistance between the, I forget whether it was A or B that they used on one of them, and then the wiper terminal. And they could see the resistance. And as they twisted the adjustment knob, it would go between, you know, about 0 ohms and about 10 kilo ohms, 10,000 ohms. And then they, after taking those measurements, it's explained, hey, this wiper contact is actually connected to the adjusting knob, and it touches a long resistive element that goes all the way around the, it's in blue in case you can't see my mouse very well. And again, I'm sorry about that. My mouse used to be nice and large, so I'm going to need to Splunk for the zoom setting for that. So this resistive element is long, and the wiper terminal is going to touch it corresponding in a position that's corresponding to where you've turned that adjusting knob. And so then, you know, maybe you'll see 2K on one end and 8K on the other to make a total of 10K for the 10K potentiometer. And if you turn it to the part, you know, in the other direction, you might see 2K and 10 and 8K on opposite ends. And so then the students go through and they do more voltmeter or more resistance meter measurements and fill in a table. And so they get to know it better, and they also find out, hey, potentiometers are inside joysticks. And that's how they, when you push the joystick knob, it rotates the potentiometer. And so it has relevance to their gaming lives. And then they connect power to the A and B terminals. And after that, instead of measuring resistance, they start measuring voltage, because with the A and B terminals connected, it's a really handy dandy thing that the potentiometer's wiper terminal, which is now connected through a resistor to P4, will have a voltage that's very measurable. And then one thing that's kind of fun is after measuring the voltage and adjusting the knob and seeing the voltage change, is you can also plot it with the oscilloscope. Now, I'm going to run this first to make sure that I don't break all your, okay, and this is a little different. Since it's in a Google Doc, you end up following the link and then downloading from here. Okay, and I'm going to put this link on another screen first. Okay, so bear with me while I go through this. I just want to make sure that we don't have another hiccup with the Cyberscope. Whoopsie, that would be a hiccup. Control Z. Paste. Okay, download. All right, then I'll open it with the editor and flash it and then disconnect. Go back to the Cyberscope, hit connect, choose the embed serial port. Okay, so that's looking good so far. And then what I have to do is brighten this up a little bit first. And then I've got to put my my voltmeter cables back on. And the black alligator clip needs to go to ground. So anywhere it's socket next to a blue blue line is fine. And then I'm going to put the red probe right in P4. So that is the socket next to the P4 connection. And after doing that, it's possible to adjust the potentiometer knob and see the plotted voltage going up and down. Okay, now that I know it's safe, we'll go ahead and give you a link to this download of the hex file. You can try that out yourself. Okay, how are we doing? Let me know when you have some success by giving me a thumbs up, either in using the reactions buttons or chatting me.
I think that's the hex code again, and I can't download it out of the chat. I can only
Okay.
copy.
So when you copy and try copying that link, shade it and then right click and select copy, and then go to your browser and then paste it in. And it should give you a black screen that allows you to download.
Okay, yeah, I can do that. Thank you.
Good, good. And then once you've downloaded it, then just drag and drop it into the python.microbit.org editor, connect, flash, disconnect, and then go to Cyberscope and connect.
Andy, where do the probes go again for this?
Ah, okay. So the probes go, let me see if I can get you a good picture of that. Okay. Plot potentiometer. Oh, it's because it's the same as in measuring the voltage. Okay. So what we're doing here is we're putting it in at the potentiometer. If you so it's row 29, and right where the resistor and the potentiometer meet. I actually put mine in the same row as the P4 socket over at the edge adapter. Either way is fine. And then you want to have your black probe just connected to ground. So by the blue stripe, or in this case, by the B terminal.
Okay, got that to work.
Excellente. So have we all, or at least most of us, gotten some plotting of potentiometer voltages? As you twist the knob, you can kind of make the line rise up and fall back down. So rising with clockwise, and then falling with counterclockwise, and then back and forth. Kind of looks like the stock market. I guess with the stock market, what we really don't want to see is this kind of thing.
Feels kind of like a Etch-a-Sketch.
Yeah. The problem there is that it doesn't clear it when I shake it. But yes, I agree. It's a kind of like a digital Etch-a-Sketch. For those of you who have finished that, I'm going to paste in one more, which is a potentiometer controlled servo, and you'll be able to twist. So we have potentiometer controlled light, potentiometer controlled oscilloscope plotting, and the students, incidentally, when they're plotting the measurements, we challenge them to plot some different we challenge them to use the potentiometer to kind of get an understanding of what they're, the physical relationship and how that can be graphed, the relationship of physically where the potentiometer has been rotated. And then we challenge them to make some common waveforms like the square wave and the sine wave and a linear decay. And then we talk about real oscilloscopes.
Challenge them with a Lisa-Jew.
Yeah, so I don't have that. So the Lisa-Jew or Lise Schwa was a way I've heard it pronounced too. I'll have to look it up on Wikipedia to find the right one. That is a feature that is not supported currently by the Cyberscope. I've got some things to work on here. There's quite a grocery list of features I'd like to add, and that's one of them. It's a different form of plotting, and it's that I will skip because it's out of the scope of what I want to talk about, which is potentiometer controlled. There's a potentiometer controlled light, and then servo motion is here, and the script is rather concise. Oops. Copy. So here's the potentiometer controlled servo script in your chat window. And that's kind of a fun one to do. Make sure to disconnect from your Cyberscope before going back and connecting with your microbit editor. Okay, and then what you can do is your servo will assume a position that corresponds to where you have twisted the potentiometer. And as you can see, as I twist the potentiometer, the servo horn follows along. I think that's kind of a fun one. And the students are challenged to scale it. They're also, instead of solving for 2 equations and 2 unknowns, they're given a map function to save them some work. So this map function, all you do is give it the endpoints of the input and output ranges, and then it maps whatever value you have from where it would be in your input range to your output range. And so that's how we, at this point in the textbook, start going away from y equals mx plus b, because the students will have already have solved that several times. It really does a nice job of tracking, I think. How about you guys? How'd it go? Got 1, 2 thumbs up. Thank you. Is it working, Kurt? Excellent. Okay, just give me a shout out if you need any help with that one. Pretty neat. I agree, Anna. Thumbs up from Nelson. Excellent work, everybody. Okay, so I did kind of skip around and we did a little bit more with push buttons. I guess I would just like to point out on the push buttons that there's some measurements that are taken, and the students do look inside the push button to learn what's going on. And so so that they add a push button, they take continuity measurements on a push button that they've added to discover that, you know, the two side pins are kind of the same, kind of connected all the time. So these two rows are actually connected. And after taking those measurements using the continuity tester again, what they do is they find out, okay, well, the reason that it looked like the rows on both sides of the push buttons are connected is because they really are. There's a wire that passes all the way through the case of the push button. And so when you plug it in, you're shorting two rows of 5 to each other on both the upper and lower pins. And then there's a little push button with some metal that connects over it. And when you press it down, it shorts the upper wire to the lower wire. So everybody's connected to each other. And after some more measurements, they get to measure the voltage to see that it's 3.3 volts when it's pressed and 0 volts when it's not pressed. And they learn about how an extra resistor is added to either pull down the resting voltage or pull it up when the button is not pressed. And without that resistor to either pull it down to 0 volts as a resting state or up to 3.3 volts as a resting state, what happens is that you have an antenna that can be affected by the static electricity that somebody picks up by dragging their feet on the carpet. And there's also some more, looking for the diagram. Maybe it was here. Yeah. So there's a diagram and a little movie and written explanation that talks about what voltage is where when you have the button pressed or not, and what read digital returns to store in a variable. And we pick the name state in this case. And so this is helpful along with the measurements the student takes. They get a better idea of what's going on inside the push button and why the circuit works the way it does, because it is a little bit of an elusive circuit. It's deceptively simple. All right, so I hope that's been fun. And what I'd like to do is talk about, there's a lot more that can be done to expand this book as time permits. Right now I'm finishing off and we're working on posting the potentiometer chapter. And as you can see, I'd like to do a lot more with it. And you have parts in your kit that will support all of these activities. Then just a reminder that for shopping at Parallax, it's just www.parallax.com, and then you can click shop. When you do that, you will see categories on the side. And microbit, for example, is one of the categories where you can see all things microbit and microbit kit oriented. Also, the student, oh yeah, and then like one of the product categories here is microbit. That's the web address when you click it. The student and teacher resources are at learn.parallax.com. And so the workbooks are right here in the first page. And then for you, you can go to the educator resources. This is the textbook for the What's a Microcontroller kit as it stands. There'll be a new one, the potentiometer one appearing, but you do have a link now to the draft if you wanted to use it. Please don't share that one out with students. It has solutions in it that have not been culled yet. Documentation, here's a link to the microbit documentation. And also a reminder that there's fun things that the students can do with just the microbit as a warm-up and to learn the Python programming language. And that there's more in a YouTube video, a couple of YouTube videos that I have recorded that talks about the curriculum available with the microbit, computer science, and much more. This is learn.parallax.com/educators. That's where you can go to get the assessment materials. Another place that has nice microbit resources is cyber.org. And let's see, how much time have I got? 12 minutes. And so we can go to cyber.org. And then since one of cyber.org's big directives is cybersecurity, I'm going to take this off screen while I log in. Oh, actually, before this, cyber.org offers a curriculum to teachers in the United States for support of United States classrooms. If you already have access, you can just log in. Otherwise, there's a sign up link, and you need to prove that you're a K-12 teacher in the United States in order to be granted access. An email to them if you're doing work for K-12 teachers might get you access. I don't know exactly what their rules are. And so I'm going to log in here real quick. Okay, so after logging in, your dashboard will look like this. And there's lots of great subjects here. The coding fundamentals, I believe, is where you'll see microbit material. And they offer it in both make code block, that's the block programming for the younger crowds. And so they have intro projects and then even some cybersecurity material. We have cybersecurity material as well. And then there's also the Python equivalent with the same stuff. All the way down to cybersecurity content. And so this is mainly like teacher notes worksheets. They have some slide shows for you. This is all teacher material, not well, it'll say specifically if it's a student worksheet. Otherwise, you know, teacher notes are kind of like what we offer, where you'll want to not share those out with the students. And that's as you can see, cyber.org has quite a few different topics. If some of the other classes that you're teaching, you might find something that's useful there. For those of you who have the Cyberbot, by the way, cyber literacy has some additional material above and beyond what Parallax has. And so here it is in the Cyberbot section. They also do the ShieldBot and the BowBot robot. And yes, I see some discussions about do we offer tutorials for make code block? And the answer is no, just Python at this point. Here is the Cyberbot robot. The microbit has made the Cyberbot robot quite a lot of fun because, you know, especially with all its built-in features, the radios really are what makes robotics kind of extra entertaining when you have a microbit as the robot controller. But in general, in robotics, it gives a nice physical manifestation of your script. So here's a script that has the robot go straight ahead and then turn. And as an example of a computer science lesson with a physical manifestation, learning about for loops and how to repeat a routine a certain number of times will get you from a straight ahead and a right turn times 4 gives you a nice square in navigation. With the Cyberbot, you can also build circuits like here's Whiskers, which is a bump into sensor. Here is a light sensor that comes with it. And it follows the light. We also have a non-contact object detector, which is infrared light emitting diodes coupled with infrared receivers. And it shines an infrared flashlight ahead. And what's really neat is when you get to when you start using the radios. I'm going to back this up. Okay, so what we have here is a whole class full of Cyberbot robots. And then over here, we have a computer with 1 microbit connected to the whole class of robots. And this microbit is the only transmitter. The rest are running scripts that are receiving. And so the transmitter is taking speed values from the terminal as well as a certain number of milliseconds to run the script. And then you actually, by broadcasting the speed and runtime commands, you can get something interesting like the synchronized dance here. So those are some examples with the Cyberbot robot. It's a really great educational tool. I'll show you there's lots more there also. Let's see here. So at learn.parallax.com, for those of you who are interested in the Cyberbot, there's a whole chapter down here. Copy link address. And this chapter takes you through similar prerequisites to what we did, except for there's also more computer science content focusing on many of the features of the microbit. Dictionaries, exception handling, strings and characters are some examples, and they feed in later to cybersecurity content with the Cyberbot robot. And then there's all the basics that come with the kit, like building the touch navigation or the light navigation, the infrared, and then we get radio basics and radio and data. So you can send messages, or you can send groups of messages that, for example, tell the robot how to navigate with a keyboard over the radio. That's where the radio data comes in. There's also tilt control, which is kind of neat. A lot of students like this for, say, SumoBot activities where you can tilt and control the speed and direction of the. So basically, however this microbit is tilted, it radio broadcasts that tilt information to the Cyberbot, and the Cyberbot receives it and parses it and figures out how fast each of its servos should be set to. So here is contact info for Parallax. We've got an educator hotline, especially if you're have something going on where your students are possibly waiting for you and need an answer or some troubleshooting. That's a good one to call. We also have sales, their phone number and email for purchase orders. That's the place to contact. Education@parallax.com is, well, Stephanie, Ari, and I, all three get a copy of that, along with our senior software engineer and a couple other folks. And so basically we decide amongst ourselves who the best person is to answer your question if you email education@parallax.com. So that's a great, great resource. And then here's our Facebook link. This a lot of this was, the development of some of this was underwritten by, or part of the development of the Cyberbot and the curriculum we just went through over this workshop was underwritten by cyber.org. So we'd like to extend our thanks to them and encourage you to get involved with them. And then also we are Parallax, and thank you for coming. Shall we go ahead and stop the recording and move to questions and answers and tech support?